Your power station has less than 1 hour left, and you don't even know it yet. The grid just went down in the middle of a heat wave, and the device you trusted to save you is already losing the fight. Nobody warned you that the box on your floor, the one that cost you $600, was never built for this. It is failing quietly, without warning lights, without an alarm, and almost nobody watching it understands why. This is the moment that separates a manageable emergency from a medical one, and it happens inside the first hour, long before anyone expects it. In the next few minutes, you'll understand exactly why it's failing and what actually keeps a family alive when the power stays off for days, not hours. The failure starts with a number almost nobody checks before buying a power station. A small window air conditioner pulls somewhere between 1,000 and 1,500 watts just to keep running, and central air systems pull far more than that during startup. A space heater draws close to 1,500 watts on its own, almost every single unit sold in stores. A typical consumer power station holds between 500 and 2,000 watt-hours of stored energy. Do that math out loud, and the picture gets grim fast. A 1,500-watt heater on a 1,000 watt-hour battery gives you around 40 minutes of runtime, not the all-night coverage people assume they are paying for. This is the battery illusion, and it is the single most dangerous misunderstanding in modern disaster preparedness. People do not die because they lack a power station. They die because they trusted it to do a job it was never built to do.
Most buyers misread the specification sheet the same way every time. They see the watt-hour number and treat it like a fuel tank, assuming it scales the way a car battery does. It does not. Watt-hours measure total stored energy, but the draw of a climate control device is what actually determines how fast that tank empties, and heating or cooling appliances are some of the most electrically hungry devices in an American home. Refrigerators cycle on and off and average out low. Heaters and air conditioners run continuously, fighting a temperature differential that never stops, which means the draw never really lets up either. That continuous draw is what quietly murders a battery's stated runtime. The hidden science underneath this is thermodynamic, not electrical. Heating or cooling a space means fighting a constant transfer of energy across the building envelope, through walls, glass, and gaps 24 hours a day, and every watt spent fighting that transfer is a watt the battery cannot get back until it is recharged. Solar recharging under real-world clouds and short winter daylight often delivers a fraction of a panel's rated output, sometimes below 30% according to Department of Energy's solar performance data. That means a power station drained overnight rarely gets a full recharge from a portable panel by the next evening. The math never balances in the appliance's favor, and multiple disaster response reviews from FEMA and NOAA following prolonged blackout events have documented rising indoor heat injuries, specifically among households that relied on undersized generators or power stations for climate control rather than building-level strategies. The survival implication is direct and uncomfortable. Any plan built around powering an air conditioner or a space heater through a multi-day outage is a plan built on a battery that will die long before the emergency ends. The people who survive extended outages without harm are not the ones with the biggest battery. They're the ones who shifted the entire strategy toward the building itself, using the structure as the primary thermal tool and treating stored electricity as a last resort for medical devices, phones, and small fans. That shift in thinking from battery-dependent to building-dependent is the foundation everything else in this breakdown is built on. And it starts with a concept most homeowners have never once considered: the thermal mass sitting silently inside their own walls. Every wall, floor, and slab of concrete in a house is already storing energy, whether anyone planned it that way or not. This is thermal mass, and it is the same principle that keeps a stone church cool in July and a cellar warmer than the outside air in January. Dense materials like concrete, brick, tile, and even drywall absorb heat slowly and release it slowly, acting like a flywheel that resists sudden temperature swings. During a blackout, this flywheel becomes the most powerful climate tool in the house, and it costs nothing to use because it requires no electricity at all. The mistake almost every household makes is ignoring this mass entirely and trying to condition the whole air volume of the home instead, which is exactly backward from how thermal mass actually works. The overlooked science here is that thermal mass has to be charged deliberately, the same way a battery does before an outage begins. In winter, this means running the heat a few degrees warmer than normal in the hours before an expected storm, letting concrete slabs in interior walls soak in that warmth so they radiate it back out for hours after the furnace stops running. In summer, it means the opposite, cooling the house down hard before a predicted outage so the walls and floors are holding cold air in reserve, then sealing the home to slow the return of outside heat. Structural engineers call this preconditioning, and it is standard practice in passive house design, a building method that keeps homes livable for days without active heating or cooling at all. Evidence for this comes directly from passive house and superinsulated building research, where homes built with heavy mass and tight envelopes have been documented maintaining livable interior temperatures for more than 48 hours after a total loss of mechanical heating, even in freezing outdoor conditions. The same principle explains why old stone farmhouses in Europe survive winter power failures far better than modern lightweight framed homes, despite having no modern insulation at all. Mass, not technology, is doing the work. The most effective winter application of this principle is what preparedness communities call the tent within a room method, and it is not a gimmick, it is basic heat loss reduction. A large room loses heat proportional to its volume and surface area. So if a family retreats into one small room, drapes blankets or a tarp over furniture to create a smaller enclosed air pocket, and seals that pocket with body heat and maybe a single candle or a rated indoor safe warmer, the volume of air that needs to stay warm shrinks dramatically. Emergency management researchers have long noted that a single occupied room, properly sealed, can stay 10 to 20 degrees warmer than the rest of a house with zero additional heat input, purely from trapped body heat and reduced air volume. The survival implication scales directly with duration. Short outages barely test this system, but outages lasting 2, 3, or more days are exactly when thermal mass and volume reductions separate comfortable households from dangerous ones. A family that pre-charged their walls with warmth and retreated into a small sealed room is fighting a losing battle far more slowly than a family trying to heat an entire 1,500 square foot house with a single space heater running off a dying battery. And once that foundation is in place, the next layer of defense has nothing to do with heating or cooling equipment at all. It has to do with air movement and the physics of a principle called the stack effect. Heat rises because warm air is less dense than cold air, and that single fact is the basis of one of the oldest passive cooling techniques in architectural history, the stack effect. Warm air inside a structure rises in pools near the ceiling and upper floors, while cooler air settles low. Opening a window high in the house, combined with an open window low in the house, creates a natural chimney of moving air, pulling hot air out the top and drawing cooler air in the bottom, without a single fan or watt of electricity. This is not folklore. It is documented building science, used in naturally ventilated architecture across hot climates for centuries, from Mediterranean courtyard homes to traditional buildings in the American Southwest. The misunderstanding most people carry is that opening windows during a heat wave makes things worse, so they seal the house completely and try to survive on stored cold air alone. That instinct is correct only during the hottest hours of daylight. Once outside temperatures drop below indoor temperatures, usually in the evening and overnight, the stack effect becomes the single most powerful cooling tool available, exchanging the home's overheated air for the cooler night air far faster than any fan could manage alone. The timing of when to seal and when to vent is the entire skill, and almost nobody teaches it.
Evaporative cooling adds a second layer with almost no equipment at all. Water absorbs a significant amount of energy as it changes from liquid to vapor, a principle called latent heat of vaporization, and this is the same physics behind sweating, swamp coolers, and desert wind towers. A simple wet sheet hung in a doorway or draped near an open window pulls heat out of passing air as the water evaporates, dropping the effective temperature of the air moving through a room. This works best in dry climates and loses effectiveness in high humidity since evaporation slows when the surrounding air is already saturated with moisture, which is an honest limitation worth knowing rather than ignoring. In dry heat regions of the American West and Southwest, this single technique has been used for generations, long before mechanical air conditioning existed at all, and it remains genuinely effective today. Historical evidence supports both techniques heavily. Traditional desert architecture across the American Southwest and centuries of vernacular building design worldwide relied almost entirely on stack ventilation and evaporative cooling to keep interiors livable through extreme heat without any electrical input whatsoever. Emergency cooling center guidance from public health agencies during modern heat waves has increasingly incorporated these same low-tech methods for households without air conditioning access, precisely because they scale to zero power availability. The survival implication is that cooling a home during a blackout is not a binary of having air conditioning or suffering. It is a layered strategy, timed to the hours of the day, that combines pre-cooled thermal mass, strategic window management following the stack effect, and evaporative assistance where humidity allows it. None of this requires a single watt, which means none of it depends on a battery that might already be failing. But even this layered approach has one more enemy to deal with, one that arrives silently through every window in the house: direct solar radiation. And the reason a sheet of ordinary aluminum foil might be one of the most underrated survival tools in the country. Sunlight striking a window does not just illuminate a room, it delivers direct radiant energy that converts to heat the moment it hits an interior surface, a phenomenon called solar heat gain. Building scientists measure this precisely, and it is why a parked car with closed windows can become dangerously hot within minutes, even on a mild day. A home's windows behave the same way, acting as unshielded collectors that dump heat into the living space hour after hour, regardless of indoor air temperature settings. Most people assume the enemy is outdoor air temperature, and it is, but a huge share of daytime heat load actually enters through glass as direct radiant energy, not through walls at all. The overlooked fix is a reflective radiant barrier, and the same emergency space blanket sold in every survival kit for warmth doubles as one of the most effective heat rejection tools available, simply by facing the reflective side outward toward the window. Reflective materials, including household aluminum foil, work by bouncing radiant energy back outside before it converts to heat inside the structure, rather than trying to absorb or fight that heat after it has already entered the room. This is the same principle used in reflective roof coatings and radiant barrier insulation installed in attics across hot climate states, technology backed by decades of Department of Energy building efficiency research. The evidence for this is substantial and well documented. Radiant barrier attic installations have been shown in Department of Energy field studies to reduce attic heat gain significantly during peak summer conditions, and the same reflective principle scales down to a single window covered with foil or a space blanket during an emergency. Vehicles using reflective windshield shades demonstrate the identical mechanism at a smaller scale, keeping interior temperatures measurably lower than unshielded vehicles parked in direct sun. Applied to a home during a blackout, covering south and west-facing windows, the ones catching the most direct afternoon sun, with reflective material, can meaningfully reduce the heat load the rest of the passive cooling strategy has to fight. The survival implication compounds with everything already covered. A home that pre-cools its thermal mass, manages ventilation through the stack effect at the correct hours, applies evaporative cooling where humidity allows, and blocks solar heat gain at the window before it ever enters the room, is fighting the heat wave on 4 fronts simultaneously, using zero stored electricity for any of it. That reserved battery power stays available for the one thing it is actually suited for: keeping a phone charged, running a small fan directly on a person, or powering a medical device that cannot be replaced by any passive technique.
Every technique covered here shares a single underlying pattern, and recognizing that pattern matters more than memorizing any individual trick. Modern preparedness culture has been sold a narrative that technology, specifically batteries, generators, and powered climate control, is the primary line of defense against extreme temperature emergencies. The evidence points the opposite direction. The building itself, its mass, its ventilation pathways, its window exposure, is the primary system, and stored electricity is a secondary support tool with real hard limits that most people never bother to calculate until the emergency is already underway. The households that come through extended blackouts safest are consistently the ones who understood their home's passive behavior before the outage started, not the ones with the largest battery in the garage. This matters because climate volatility and grid strain are both trending in directions that make multi-day outages more common, not less, according to repeated infrastructure resilience assessments from federal energy agencies. Aging transmission infrastructure, increasing peak demand during heat waves, and more frequent severe weather events are converging in a way that puts more households at risk of extended power loss during exactly the temperature extremes when climate control matters most. A battery bought today, sized for a normal evening thunderstorm outage, will not meet the demands of a 4-day heat dome or a week-long grid failure, and no amount of wishful math changes that physical reality. The final warning is this: preparedness is not a purchase, it is an understanding of the building a person already lives in. The walls, the windows, the room layout, and the timing of when to open and seal a house are tools that cost nothing, require no charging, and never run out of stored energy. Learning to use them before an emergency arrives is the difference between riding out a blackout in manageable discomfort and facing a genuine medical crisis when the battery indicator finally hits zero. The real secret was never the battery, it was the building, and it was there the entire time.